Hey everybody, Mr. Judson here. So we have done all the integration stuff that we're going to do. You might ask the question, do we really do everything? Are there possibly some integrals out there that we haven't covered? And the answer would be yes. And actually the next section that we would normally do would cover that. But we're going to skip that section. And what it's called is integration by tables. And so what you get is, if you get a problem that you don't recognize how to do, then you go to this table right here, and there are all kinds of formulas. So what you do is you start looking your way through these formulas until you find something that matches. Even our basic integration formulas are in here. Like, right here, 1 over u du, that's a u prime over u, so that's a natural log of absolute value of u. But then we've got all kinds of other things that are in here, and patterns. And here are 2 more pages of formulas. And another page of formulas. It goes up to 100. I don't think this is everything. I feel like when I took calculus in college, I remember like 8 pages worth of formulas. I don't know how many there were, but there were a lot. And we actually had to take a test over this where we would just get some random integral and we had to go through this table and find a situation that matched and then answer the problem based on that. So yeah, we're going to go ahead and skip that. I'm sure you guys are really disappointed. And what we want to look at, kind of the last thing, and then we're going to start reviewing for our Central Washington final, is finding the area underneath a curve, which we've done. But the one condition is that the x-axis acts as an asymptote. And what we want to do is, if we call this f of x, we want the integral from 0 to infinity of f of x dx. What's the area of this region right here? Well, probably most people are thinking, geez, duh, Judson, if you're going to go off to infinity, that means forever. The answer is infinity, right? Wrong. What happens is this area actually approaches some number. It converges, that's kind of the key word, it converges on a certain amount. And so that's what we want to look at for today. Now, if the asymptote was not the x-axis, if it was, let's say at y equals 1, well, now you've got an infinite amount of area here, and sure, the answer would be infinity. Or same thing, if there was a vertical asymptote and this graph turned and went up, and we had an infinite amount of area here, well, then we couldn't do that problem. Okay? So usually the way the question gets asked here is does the area converge? Okay, does it converge on a certain number? So let's take a look at a problem here. Let's say I've got the integral from 1 to infinity of 5 over x cubed dx. And so when I look at this, I'm just going to think, let's just solve it in the normal way. Okay, I would probably rewrite this as the integral from 1 to infinity of 5x to the negative third dx. I could move that 5 to the outside if I want, but I'll just leave it there. And so now what I want to do is add 1 to the exponent. So that'd be 5x to the negative 2. Divide by the new exponent. And then evaluate that from 1 to infinity. Which that would equal, let's see, first of all, if I kind of rearrange things here, I've got a negative 5 halves. That x to the negative 2, that should drop below the fraction bar. So we're going to have that right there. And now we'll evaluate that from 1 to infinity. So if I plug in infinity first, I get a negative 5 over 2 times infinity squared minus what I get when I plug a 1 in, which would be a negative 5 halves. And so we know that, when your denominator gets really large, this fraction gets really small, so small that we might as well consider it to be 0 plus 5 halves, which means my area is going to converge on 5 halves, or 2.5 square units. And you got to include the label here because that's what we're talking about. We're talking about area. Does the area converge? That wasn't too bad. Kind of painless. Compared to what we did yesterday, that really wasn't bad. Let me give you guys one to try. So we've got the integral from 0 to infinity of x minus 1 times e to the negative x dx. You guys go ahead and give it a shot. All right, so if you're still staring at this going, yeah, right, Judson, might want to think integration by parts, right? Now, I look at this and I think the derivative of this is 1. That's not what I have here. The derivative of this would be e to the negative x times the negative 1. That's not what I have here. So I've got to use one of those methods from chapter 8. And I know that when I have something I can take the derivative of and it gets simpler, and I see e to the x's or sines or cosines, then that's a good option for integration by parts. Maybe even the tabular method. Give you a couple extra seconds here to try that. Alright, so if I go over here and I think sine, I've got my u value, I've got my dv value, and I'm going to make a chart. We start with plus and then alternate. This is going to be x minus 1, so you take the derivative, you get 1, take the derivative again, you get 0. That's as far as I need to go. E to the negative x, if I was going to integrate this, so think of this integral right here, e to the negative x dx. If I let u equal this, then du is going to be a negative 1 times dx. And then I know the integral of this is just the same thing. So what that does is it gives me a negative sign out in front. And then I do it again, and I'm back to e to the negative x. And I do it again, and I get a negative e to the negative x. And so now what I need to do is I just need to, I don't want to use this first term. I'm going to go across and then use that one. I'll use these. Once I get to here, I get 0. So there's only going to be 2 terms. So my answer to this problem is positive times a negative. So that's a negative x minus 1. Since this exponent's negative, I'm just going to go ahead and drop it down below the fraction bar. And then here I've got a negative. And then 1 over e to the x. And then we're going to evaluate that from 0 to infinity. So if I plug an infinity in, I'm going to get infinity minus 1. That's infinity. E raised to the infinity, that's infinity. I almost have to think of this kind of like a limit. What's the limit as x approaches infinity? And when you get infinity over infinity, that means we want to use L'Hopital's rule. So now I'm going to think derivative of this would be, I still have the negative sign out in front. Derivative of this would be 1. Derivative of this would be e to the x. And now when I plug infinity in there, I get 1 over infinity, which is 0. And here I get minus 1 over infinity, minus what we get when we plug a 0 in. So if I plug a 0 in, I get negative 1. the negative of a negative would be positive, and e to the 0 is 1, so 1 over 1 is 1. Plug a 0 in here, I get 1, so minus 1 over 1. And so my answer is 0. That's what the area converges on. So let me take a look at a graph of this and see what that looks like. Because if this is the answer, what that tells me here is that this graph must drop below the fraction bar. Or maybe it starts above and then drops below. So there's some area above and some area below, and they kind of zero each other out. So I know it's hard to see, but let me just go ahead and do this on the TI-84. Don't forget, Thursday at 10 o'clock, that's when I'll be there, which is today's video, so if you're watching this after 10 o'clock, you missed it. Yeah, you cannot take the test until I have your TI-89. Alright, so x minus 1 times e raised to the negative x. And for my window, I'll just go 0 to, I'm not going to go to infinity, but let's just go 0 to 20. Yeah, so I don't know if you can see this, but it does start below, comes up, hits the x-axis, it looks like at 1, and then it goes up and turns and comes back down. So if I found the area from 0 to 1, let's just try that. Remember, you can do a numeric integral on the TI-84. Numeric means when I have limits, I can figure out what the answer is. So I'm going to do that from 0 to 1. See what I get. So I got a negative 0.368. And now I'll do the area from 1 out to 20. So we'll do that again. Option 7, we're going to go from 1 to 20. Positive 0.368. So yeah, there's a little bit of area above, a little bit of area below, and they cancel each other out, and that's why we got 0. So does the area converge? Yes, the area converges on 0. Square units. Alright, let's try another one. Alright, you guys go ahead and try this one. So I guess what I see first is substitution. And the reason I see that is, remember I told you guys, I always think, what's the derivative of this? What's the derivative of this? Okay, I see a fraction, but u prime over u is out of the question because the derivative of x is just 1. So I think, what's the derivative of a natural log of x? That's 1 over x, and that's actually what I have written here. If I rewrite this like this, natural log of x times 1 over x dx, well then I could let u equal this right here, and here's my du. So u equals natural log of x. Take the derivative of that, you get 1, just took the derivative of u. Derivative of this is 1 over x. And I just took the derivative of x. So really this is just the integral of u du, which would be u squared over 2. And then I'm going to plug my natural log of x back in, so natural log of x squared over 2. And we're going to evaluate that from 1 to infinity. So let's see, the graph of a natural log, I don't know if you guys remember what this looks like, but it looks like this. And so if I'm plugging an infinity into here, that means go way out here. Well, this thing just keeps on going up forever. Not very fast, but it does go up forever. So this eventually will become infinity squared. I got infinity over 2 minus what I get when I plug in a 1. Plug in a 1, natural log of 1 is 0. So it looks like my answer is infinity. So I would say no, this does not converge. And so just, just kind of a way to feel comfortable with your answer. And this is something you could do on the Central Washington test. Graph this, see what it looks like. Do we have an asymptote on the x-axis? So let me clear this. I've got natural log of x, and then I want to divide that by x. And then let me just readjust my window here. 0 to 20, I'll say let's go from -2 to +2. Interesting. So I have another graph that does something like this. Kind of like on the last problem. Y-axis is an asymptote. And so what I want to do is I want to double check this. If I'm going to do the integral from 1 to 20, graph, second calc, option 7, we're going to go from 1 to 20. So I got an answer for that. We'll say 4.5 about. Now let me change my window. Instead of going to 20, let's go to 100. And I'll graph that. Do the integral. This time I'll go from 1 to 100, 10.6. So it more than doubled, which to me says it seems to be continuing to grow. And you could try that again, and if it's still continuing to grow, it means this area right here doesn't really converge. It's kind of weird. There is an asymptote there. Looks just like our last problem, but that area doesn't converge. This thing is going off to infinity. All right. That's what we have for today. All right, so we're now on number C19. We're doing page 585, 15, 18, 20, and 21. And that's it, folks. We're done learning new stuff. Now it's time to start reviewing, getting ourselves ready for that Central Washington test. We will do that on Tuesday next week. All right, you guys take care. Stay safe.